Today we're going to talk about Multicore OCaml, and our speaker is KC, who is an assistant professor at the Department of Computer Science and Engineering in the Indian Institute of Technology in Madras. He works on the intersection of programming languages and systems, and for our purpose today, he leads the Multicore OCaml Project, which aims to bring native supports for concurrency and parallelism to OCaml. He has experience in the domain with having worked on MultiMLTon, a multi-core extension for MLTon compiler, and also having developed some concurrency abstractions for the Glasgow Haskell compiler at Microsoft Research Cambridge. Casey, to you.
All right, thanks, Raphael, for the introduction. So today I'm going to talk about Multicore OCaml, and in particular, what I want to do is to tell you some exciting things that are in for 2021. So OCaml is a reasonably popular programming language used widely in the industry and academia. OCaml has found particular use in mission-critical software systems, static analysis tools, verification tools, as well as low latency network services. So there are lots of OCaml code that are out there, right? The millions of OCaml lines of OCaml code that is out there. For all its strengths, though, OCaml is one of the few system programming languages to lack multi-core support. And what we aim to do in this project is add support for concurrency and parallelism to OCaml. So Multicore OCaml project was started back in 2014 at the University of Cambridge. And it started by Stephen Dolan and Leo White. I joined the project in 2015. And in the last few years, the project has really picked up pace. And we have a lot of people from upstream also contributing. So I'm really hopeful that 2021 will be the year of Multicore OCaml. So one thing that we do in Multicore OCaml is we clearly delineate concurrency from parallelism. Concurrency is overlapped execution of tasks where the tasks may context switch between each other, whereas parallelism is simultaneous execution of tasks. So in keeping with this delineation, we clearly separate the mechanisms to express concurrency and parallelism in OCaml. For concurrency, we have what are known as effect handlers. And for parallelism, we have a mechanism called domains. Right? And okay, so we're adding concurrency and parallelism to OCaml, but we are not doing this in vacuum, right? So there are several challenges to adding these features to a very popular programming language. The first challenge is that we have millions of lines of legacy code that are out there. And not much of this code has been written with concurrency and parallelism in mind. Right? So if I told you today, you can have concurrency and parallelism in OCaml, but you have to refactor your code, right? In order to just keep it sequential. Because we break certain features in the language, or we change the semantics of certain features wholesale, and you have to work. I mean, the cost of doing this is prohibitive, right? So given that we have lots and lots of code, backwards compatibility is a very key design principle for us. Secondly, OCaml is a reasonably performant language. It has very good low latency and is great for applications that can tolerate around 10 millisecond latency, and is known for its predictable performance. Right. So when we add multicore to the language, we want to ensure that these good properties are around. OCaml has excellent compatibility with program analysis tools that observe the stack by unbinding the stack, such as GDB and LLDB for debugging, and perf for profiling, also other libraries, right? So we want to ensure that these system tools continue to work when we add concurrency and parallelism to the language. So the key design principle that sort of guides us is that backwards compatibility is much more important than scalability for us, because we want to ensure that the language remains usable even after we add these fancy features. Right. So given that those challenges, what would be desirable features for Multicore OCaml? So the first feature that we want is feature backwards compatibility, which essentially says that if you take OCaml code today that runs on stock OCaml compiler, and if you run it on the Multicore OCaml compiler, firstly it type checks and it runs with the same semantics, right? These are ideal goals. We of course break one or two things, but we want to get there. The second one is performance backwards compatibility, which essentially says that you have some performance expectations from your program, that it runs in so many seconds with so much memory. If you take the same sequential program, run it on the Multicore compiler, it will we aim to have the same characteristics. So thirdly, for parallel execution, we place GC latency in front of multicore scalability. And the reason why we do this is because OCaml is widely used for low latency programs. We want to ensure that OCaml continues to be a great language for low latency programs, even under multicore execution, right? And practically what this means is that we have to build a multicore capable concurrent garbage collector, which is much more difficult than a garbage collector which is multicore capable but optimized for throughput. By ordering the goals this way, we believe that we can solve the latency concern, and as a result, we naturally get throughput as a byproduct. That is our hope. And we want to ensure compatibility with program inspection tools such as GDB and perf. And last but not least, the mechanisms that we add, the concurrency and parallelism abstractions, should be efficient, right? So these are our ideal requirements. And with those requirements, what I'm going to do today is to talk about domains for shared memory parallelism first, and then talk about effect handlers for concurrent programming. Okay, so firstly, domains. Domains are our unit of parallelism. Domains are heavyweight. They map onto an OS thread. So there is a one-on-one mapping between domains and OS threads. And the recommendation is that your multicore program will have one domain per core. The domains expose a low-level API for spawning and joining domains, waiting and notifying for synchronizing between the domains. We also have an API for domain local storage. And the one key thing that we have in Multicore OCaml is that we have a well-defined memory model that explains what goes on when your program has data races. Right? In contemporary programming languages, there are two widely known memory models, multicore memory models, C++ and Java. And the OCaml module memory model is better than these models in that it is modular. Right? So I'm not going to be able to talk much about the memory model today, but I recommend interested readers to have a look at this paper that we published in PLDI called Bounding Databases in Space and Time. Okay. And lastly, we don't have any restrictions on sharing objects between the domains. Right? You can freely share objects between the domains through some shared abstractions. And the way it works is thanks to our garbage collector, which does all of the hard work underneath. And much of the work in building a multicore feature for language like OCaml is building a multicore garbage collector. Right, before we look at the multicore garbage collector, it's useful to look at how the stock OCaml garbage collector works. So OCaml garbage collector is a generational, non-moving, incremental mark and sweep garbage collector that has a small minor heap. By default, it is 2 megabytes in size, and objects in the minor heap are allocated with bumping a pointer. And once the minor heap is full, what we do is we evacuate the survivors from the minor heap to the major heap. And the major heap is collected with the incremental non-moving mark and sweep garbage collector. And the way the major collection works is that at the start of the major cycle, there's a small idle phase where the mutator can run. So mutator is a word that you find in garbage collection literature. For purposes of this talk, if you see a mutator, just think OCaml code. Right? There is an idle phase where OCaml code can run. And then we start marking the roots incrementally by switching to OCaml code and marking roots and so on. And then we continue to mark the rest of the heap. And once marking is done, we incrementally perform the sweeping. And once sweeping is done, we say that the current cycle has ended, and we continue on to the next cycle, right? This design has very nice properties. The first property is that since most of our allocations are into the minor heap, our allocations are very fast because we allocate by bumping a pointer. And because our GC is incremental, the maximum GC latency that we observe across many of our programs are around 10 milliseconds. There are outliers there, but they are around 10 milliseconds. And the 99th percentile latency is around 1 millisecond, right? This is quite enviable for a garbage collected language. And we want to ensure that we can keep these properties around when we add multi-core support. So to this end, what we do is we sort of adopt the same heap structure. We have a shared major heap and a shared minor heap. And in order to allow fast allocations in the minor heap without synchronization, the minor heap into small pages. And each will request a page and has a domain local allocation pointer that points into this page, that you can allocate by just bumping the pointer without synchronization. And once you reach the end of the page, you request another page from the minor heap, and you only need synchronization when requesting this page. And once you exhaust the minor heap, we trigger a minor garbage collection. And the way we do that is a stop the world parallel garbage collector. So what this means is that once you exhaust the minor heap, we see all of the domains, right? All of the domains cooperatively evacuate objects from the minor heap, the survivors from the minor heap to the major heap. And you need two barriers for doing this, one at the beginning of the minor heap and one at the end of the minor heap. And in our experiments, we observed that on 24 cores, this introduces 10 millisecond pauses, which is roughly on the same order of pauses that we see in sequential programs as well. So what about the major garbage collection, right? Our major heap is collected with the mostly concurrent mark and sweep garbage collector. And the schematic is given in this slide. And what you should observe is that each domain alternates between performing the garbage collector and running the mutator. And there are a few things that you can observe. Firstly, when one domain is running the mutator, another domain could be doing garbage collection, right? And you don't need any synchronization between that. And when one domain is doing marking, another domain could be doing sweeping. We also don't need any synchronization there. And the only synchronization that we need is at the end of the major cycle, where if you ignore finalizers for the moment, all we do at the end of the major cycle is all the domains just agree that all the work that is necessary for the cycle is done, and we can continue with the next cycle, right? And because OCaml is a real language, we have advanced data structures such as mechanisms such as finalizers, ephemeron, weak references, and so on. So in order to support this, in the worst case, we need 3 barriers per major cycle, right? And 2 of these barriers are required for 2 different kind of finalizers in OCaml. And the key thing to notice here is that in the stop the world sections in the major cycle, we don't actually do any work. We just test whether we've done all of the work, right? So our major cycle pauses are actually smaller than the minor cycle pauses. And on average, it is around 5 milliseconds on 24 cores in a set of benchmarks that we have. So, okay, so that's the GC. I had earlier mentioned about performance backwards compatibility, right? So if you took your existing benchmarks today and on the, how does it perform? So the graph here shows normalized time of the multi-core OCaml compiler against a sequential baseline. And we have a large collection of benchmarks here, which is part of the Sandmar benchmarking suite. And it has real-world benchmarks already, right? So it has Ermin, it has Menhir, Pop, and Alt-Ergo. And the graph here should be, because we are showing the normalized time, right? Ideally, the graph should, none of the bars should be visible, right? Which just means that the multi-core OCaml compiler has the same performance expectation as the sequential, the stock OCaml compiler, but we do see some differences. And the way to read these is that whenever the bar points down, the programs run faster the sequential program runs faster on the Multicore OCaml compiler. And when the bars point up, the sequential programs run slower on the Multicore OCaml compiler. And the high-level takeaway is this, right? If you took your sequential programs today and you ran it on the Multicore OCaml compiler, they will be around 1% faster. And the difference is mostly under the measurement noise, right? Measurement noise that we have in the experiments. And the outliers are due to the change in the allocator. So the multicore allocator is different from the sequential OCaml, stock OCaml allocator, and hence we see the differences. But this is sort of evidence of performance backward compatibility that we wanted to achieve. Okay, that was sequential program, right? And the whole reason for building Multicore OCaml is to write parallel programs. So the thing that we observe is that the API that is exposed by the compiler is too low level for the end user. So what we have done is we have developed a library called domain slip, which gives you a higher level abstraction over domains. In particular, it gives you a taskful abstraction, which allows you to share tasks between the domains by work stealing. And we have a async await mechanism for recursive nested parallel programs. And we have a parallel for OpenMP style parallel for reduce and scan for writing programs that are amenable to that sort of parallelism. So let's look at examples. How do you actually take these mechanisms and write parallel programs? So the prototypical example for recursive nested parallelism is parallelizing recursive Fibonacci computation. So here is a sequential Fibonacci function. And the observation is that these recursive calls are independent. So you can spawn these off as two different tasks and collect the results and return it to the caller, right? And that is how you parallelize it. Let's see how to parallelize this program. So in order to start off writing parallel programs with domain slip, the first thing you should do is set up the pool, right? Number of domains that you provide. And the last thing you should do is start on the pool, right? And you perform the parallel work when the pool is live. And the idea is to ensure that the pool is set up at the beginning of the program and torn down at the end of the program. Setting up and tearing down the pools multiple times will add to the overhead. So how is the parallel Fibonacci function implemented? So the parallel version of Fibonacci looks at the n, right? If n is less than 40, we say that the granularity is too small in order to benefit from parallelism. So we just simply call the sequential version. And instead, if the granularity is large enough, we spawn the recursive subcalls, the two recursive subcalls, asynchronously using the async primitive. And what you get back is a promise. A and B are promises. And what you do is you await on the promises for the result, and you return the sum of the results, right? And as you can observe, this parallel program sort of acts same structure as the recursive sequential recursive version, except that we have async and await at strategic positions, right? And FibC is simply the sequential Fibonacci program, and that is the entire program for parallelizing Fibonacci. And let's see how this performs. So what we are doing here is we are computing the 48th Fibonacci number, right? And we ran it on a machine with 24 physical cores. And we see that we get around 17 times speedup. And the speedup is roughly reflective of what you will get with similar programs. Okay, that was nested parallelism. So next, we'll look at an example for using parallel for. And the example that I pick here is Conway's Game of Life. And if you don't know Conway's Game of Life, it is a zero-pair game, right, with a 2D grid. And each grid is either alive or dead. And the game proceeds in steps, where the next cell is alive or dead based on the population of the neighbors. Right? You essentially have certain rules for whether a cell is will be alive or dead in the next step, and you apply the rules, keep on applying the rules to see fancy animations, right? And interestingly, this is known to be Turing complete. right? So, and the way we parallelize this is easy, right? So because we proceed in each step, we can, and we use the previous board to compute the next board. We can split the board into rows that we distribute among all of the domains, right? Which compute the work and collate the work for the next step, and we keep repeating this. So the way we actually write the parallel version of the program is by parallelizing the inner loop. Inner loop iterates over each of the cells and computes the value of the cell in the next step, right? And all we do here is replace the outer sequential for loop with the parallel for loop. We have the pool argument, which I'm sort of ignoring now, set up and tie down the pool. But otherwise, the start and the finish stays the same, the body stays the same. You just have to replace sequential for with parallel for. And that is the entire parallel program, right? Except for setting up the parallel pools. So let's see how this works. So we picked up, we chose a board, initial board of size 1024 by 1024, right? And we randomly initialized the board and ran the game for 512 iterations. And on 24 cores, we see that we get around 20 times speed up, right? And we see a similar speed up on programs that do not have any synchronizations. We don't have any synchronizations across each of these for loops, right? So that's a typical pattern that you see in a lot of these mathematical kernels. We see similar there. Okay, so that concludes my description of domains for parallelism. And the next thing we're going to talk about is effect handlers for concurrency, right? As I mentioned before, parallelism is not concurrency. Parallelism is just a performance hack, right? You have a program, you want to make it go fast, you add some primitives, you make it go fast on multiple cores. But concurrency is a program structuring mechanism. It lets you express programs you cannot otherwise, right? And in fact, you can do concurrent programming today in OCaml using libraries such as LWT and async. And what these libraries do is do asynchronous I/O, where you attach a callback to I/O operations, right? And we have some nice syntax for their callback, but essentially we have is callback oriented programming in the same way we have oriented programming in JavaScript, and we suffer many of the same pitfalls, right? Because we write in callback oriented programming, we sort of write in this handwritten CPS style, right, where we thread the continuations, the callbacks together. We don't stack, right? So backtraces are not useful anymore. And we cannot use inbuilt exceptions in OCaml anymore because they go to the wrong place, right? And we have to write our programs in this monadic syntax, which is okay. We have some syntax extensions now in OCaml to make it better, but it's still monadic, right? So other have it better. If you look at Go and GHC Haskell, they have abstractions for lightweight threads. Like Go has Go routines and Haskell has threads, which let you write programs in direct style. So I want to do the same, right? I want to have stacks. I want exceptions to be used. These sort of stacks are also useful for recursive nested data parallelism. I can't go into the details in this talk, but they are very critical for doing efficient parallel programming as well, right? So we thought about how do we make the situation better, right? Should we add lightweight threads to OCaml? Was the question we asked. And it turns out that we can actually. So we add what is known as effect handlers to OCaml, which is a mechanism for programming with user-defined effects. And what effect handlers give you is a modular basis of programming with non-local control flow mechanisms, including things like exceptions, generators, lightweight promises, asynchronous I/O, and coroutines. And what effect handlers let you do is that by adding this one primitive to the language, you can implement all of these other primitives as libraries, right? So this makes the compiler smaller, but also let you experiment with new abstractions if you wanted it. We don't bake it into the language, right? And the key reason why effect handlers are so expressive is that the effect declarations are separated from the interpretations. In the same way, exception declarations are separated from what we do when we handle an exception that is given by the exception handler, right? Because effect handlers are sort of the same as similar to exception handlers, we borrow similar syntax. So here is a program that uses effect handlers. I'll run you through this. So the first thing that we have is an effect declaration, which says that E is an effect, which when performed returns a string value. We can have computations that perform effects, which are guarded by handlers. The handler syntax here is different from exception syntax in that we have an effect keyword. We also have the effect that we are handling, and we have this additional K. I'll come back to this K. And within the computation comp, you can perform the effect. This is like racing, but it has some interesting properties. What it does is it suspends the current computation, right? And finds the matching effect, my matching handler that handles this effect, right? And the handler that handles this effect is this handler, just the handler that sits innermost handler. And the rest of the program, from the point of perform all the way to the handler, is reified into a delimited continuation, right? So the suspended computation is reified into a delimited continuation. And what you have in hand is a way of resuming the suspended computation. And we use the continue primitive to resume the suspended computation. And the way we continue is we say continue this continuation with some value. Here it is string because the original declaration said if you perform this effect E, you should get back a string. So when you resume this continuation, you give it a string, which continues the execution where it left off. Okay, so let's actually walk through the example step by step, where I will also show how the runtime system behaves in terms of how we manage the stacks for the effect handlers. So on the left-hand side, what I have is the program where I show the program counter. On the right-hand side, I have stack, the current stack. The stack pointer is currently pointing at the top of the main function. And just about to enter the effect handler, right? I call it the effect handler because the computation is here and I have an effect pattern here. So I'm going to enter the handler, right? The PC is now within the effect handler. The first thing that you do is to create a small stack piece, right? Stack chunk, and a parent pointer that points to the previous stack chunk. And we also associate the current handler, right, with stack chunk. So we call this piece of stack along with the effect handler as a fiber, right? And Multicore OCaml allocates fibers on the C heap, right? We actually malloc this fiber on the C heap, and we establish this pointer. Now the program is actually executing here. The stack pointer is in this com. So if you take a step, we print 0, right? That is what the first thing in comp is, and we are just about to perform E. So what happens when you perform E? We suspend the current computation and we transfer control to the matching handler. And what happens here is we first create reif continuation. A continuation is a small one-word object that is allocated on the heap that points to the current fiber. And we set the parent pointer to null, right? And we find the matching handler. The matching handler is the innermost one. We switch the stack to the previous stack, right? Where we get this handle to the K, which is the handle here. And our PC transfers to the matching handler. So we are executing the body of the handler now, which prints 1. And now we are just about to, I am just continue. What should happen at continue? The thing that we do at continue is, firstly, we zero out the continuation, right? We say the continuation can no longer be used because I've already used it. So what you get here is what is known as one-shot continuations. You can only resume continuations, capture continuations once. And one-shot continuations can be captured really cheaply because you don't have to copy any of these fibers around. And when you continue, what you do is you restore the parent pointer. You also set the stack pointer to the top of the fiber stack, right? And your PC goes back to where it was, where it prints 2, because 2 is the value that was transferred over. And print 3 is the last statement. It's going to print 3. And after printing 3, it's going to return back to its parent, right? So when it prints and returns back to its parent, we actually no longer need this fiber. So we free it at that point. And we return back to the point of continue. So resuming a delimited continuation is like calling a function. And call a function, the function returns. And similarly, the function returns here. We print 4, and we are done. So the whole program finishes. Okay, so that was low-level stuff. Let's implement some higher-level primitives. So let's implement lightweight threading, right? And the primitives that I'm going to implement here are the ability to fork off a new task and yield the current task so that you can switch control to the next task. So what I do here is I declare 2 effects called fork and yield. And fork effect is parameterized with the thunk. And that is the task that I'm going to yield. And when you perform fork, you're going to get a unit value back. And similarly, yield is an effect which is not parameterized. It's a nullary effect. But when performed, it returns a unit, but it has some effects, right? So which is not defined here, but the effect of the yield is actually defined, right? So you will build a computation which uses fork and yield main, and in order to run this program, you need to call the run function on the main. And we assume that we have a queue of continuations here. It's just an ordinary OCaml queue, right? Assume that I have a dequeue function which gets the continuation from the queue, and an enqueue function which pushes the continuation into the queue. And what does run do? It calls spawn on main. And what does spawn do? Spawn is going to run the thunk, like invoke the thunk within an effect handler here. So also extend match with syntax with effect patterns, just like match with syntax with exception patterns. And the idea here is that this F is actually run in a new fiber, just like I explained previously. So what can F do, right? F can run to completion. So it can return a unit value. If it returns a unit value, I run the next thing from the scheduler. And what does it do? It dequeues the scheduler queue. If you find a continuation, you continue the continuation. If you don't find anything, the scheduler queue is empty, right? So you're done. And you simply return unit, and the run function returns. If instead F actually forks off a new task, wants to fork off a new task, so you get here, right? You get to a point where you handle the effect fork, where F is the thunk that you want to spawn off, and K is the continuation of the current task. So you basically obtained a version of the suspended computation current task. And what you do is you simply say, okay, I'm going to enqueue myself in the queue, the current task, and I'm going to recursively call spawn on F so that it is created as a new fiber. And yield is simpler. When you want to yield, you get the current continuation, right, which is the current task, handle to the current task. You enqueue the current task, and you simply run the next task from the scheduler queue. Right? And that's the program. You can sort of give it nicer interface by having functions fork and yield, where the functions fork and yield simply perform the corresponding effect, right? Okay, what can you do with this? So here is a simple example. I'm writing a main function here that forks off 2 tasks, and that what the tasks do is first print a message and then yield, right? And then they print another message. And if you run this program, what you get is 1A, 2A, 1B, and if you enter the first task, which prints 1A, yields. So you go back to main task, which forks off the second task, which prints 2A. You yield again. So you go back to the first task, print 1B, that runs to completion. And you call run next, so which prints 2B, and you're done. So this is a very simple example that shows how to do lightweight threading. But the same principle applies for more complicated behaviors like asynchronous IO libraries. The key thing to take away here is that the whole code is direct style. I'm not using any monads here, right? And the user code here is not aware of the fact that we are using effect handlers underneath. everything looks like just sequential code, right? So blocking code, but magically effect handlers has let us write nice looking code. So the next example that I want to talk about is generators. Generators are these mechanisms for non-traversal of a data structure by yielding values, right? They are implemented as primitives in JavaScript and Python, and you can actually automatically drive a generator from an iterator using effect handlers. I'm not going to show the code here, but we'll use this as a performance benchmark. So the task is to traverse a complete binary tree of depth 25 using a generator, right? And this is internally going to involve 2 per 26 stack switches. We compare 3 versions. First is the iterator, which simply does the idiomatic recursive traversal of the tree. And we have 2 versions of the generator. The first one is handwritten generator, which is specialized to this tree traversal, right? Handwritten, where we do CPS translation by hand, and we also do defunctionalization to remove any intermediate closure allocations. And this is known as, we call it handwritten generator. And the last thing that we have is EH generator, which is the generator obtained through effect handlers, right? And here are the performance results. This is on Multicore OCaml. The iterator baseline ran in 202 milliseconds, whereas the handwritten generator ran in 3.76 times more slower than the iterator, and the effect handler generator was around 2.5 times slower. Right. So this is I mean, you might look at this number and say, okay, this is low. Why should I care about this? The observation here is this is capturing pure overhead, right? If you have any useful work, all of these overheads will be sort of hidden away. And the fact that you don't have to do any actual work, right? Given any iterator, you can get the generator back is what makes this really attractive. Just to give you a complete picture, right? So we ran the same experiment on Node.js, where we used JavaScript's built-in generator support. And we had an iterator that ran for 492 milliseconds, and the generator was 90 times more expensive, right? That's an order of magnitude more expensive than generator in Multicore OCaml. And the fact that this is not a privilege built-in, right? We are using effect handlers to construct the generator. We think this is a win. Okay, so the last benchmark that I want to show you is a full-fledged web server. So we extended the lightweight threading example that I had shown earlier with support for asynchronous I/O. Everybody is in that link. We compare 3 versions. One is Go using net HTTP library with Go max procs to be 1. Setting Go max procs to be 1 ensures that Go is one of the cores. We have 2 versions of OCaml web server. One is LWT based one, HTTP AF, and the other one is the Multicore one, which we call MC, which uses effect handlers but also uses HTTP AF for HTTP. And all of the numbers were obtained using Word2. So here are the throughput and tail latency results. And the way to read this is this. So here, what we do in the throughput experiment is we establish 1,000 open connections, right? And we bombard the web server with lots of requests, starting from very small number of requests up to 60,000 requests per second. And we run the benchmark for 60 seconds, right? And we measure the service rate. So we look at how many requests are actually serviced. And what we see is that all 3 versions sort of scale nicely to 30,000 requests per second and then hit a bottleneck for the language. And then all of them plateau out, right? So this shows that the effect handler version is competitive. And you wouldn't want to run your web server at the peak throughput. You actually want to run it at something like 2/3 of the throughput in the real world. So we picked 20,000 requests per second as the 2/3. For the tail latency measurements, we established 1,000 connections, right? And we set requests per second as 20,000, and we measure the tail latency. The tail latency graphs are given here. On the x-axis, you have the percentile. On the y-axis, you have the latency. And what the graph shows is that the Multicore OCaml version is the most responsive, right? And you can see similar numbers for other connection count and request count. But the performance is the least interesting bit here, right? The interesting bit is that the multicore version is actually written in direct style, right? There is no monadic syntax. We can use OCaml exceptions now because we have a stack. And the way the server works is what you study as a thing not to do, right? Spawning one thread per request but because our threads are lightweight threads, we actually can spawn one thread per request, and we can get a backtrace. We can actually stop and use GDB to get a backtrace, and we can see what the program is doing. And perf also works, right? So all of these are the benefits, right? And performance is sort of the less interesting. It is important that we stay competitive, but the programmability aspect is what we want to push with the effect handler work. So, okay, given that, what's the upstreaming plan? Right? So I've discussed domains, I've discussed effect handlers. This is a lot of stuff. How are we planning to upstream everything? So we plan to upstream domains only multicore first, and we have a lot of momentum. I think we can get it there in 2021. And the whole team is working on this domains only multicore right now. Next step is to upload upstream runtime support for effect handlers without the effect. Because we have we changed the layout of the stack, we want to ensure that none of the software breaks in the wild, right? So we will push the runtime system changes into OCaml, right? Without the fancy syntax. You can still use, but you can still use effect handlers using some low-level syntax that we will sort of expose it probably through the obj module, right? And finally, we are also working on a full-fledged effect system for OCaml on top of effect handlers. So the idea is that we will first track user-defined effects in the type. Then we will move on to tracking ambient effects, things like references, IO in the type. And at that point, OCaml becomes a pure language in the sense of Haskell, right? What do I mean by this? So if you write a function which takes a unit value, prints a string, hello world, today you will get a unit arrow unit, right? Which just says that the function takes unit, returns a unit. It doesn't say anything about the effect. But what we plan to do is that we will, the fact that this function performs an IO in the type, and the syntax is still in the works, but the idea is that the function says that I take a unit, I return a unit, but I also perform the IO effect, right? So that's where we are heading. And I mean, this is still open research, right? But we have several working versions of how this should look like. We're experimenting. Again, our concern is backwards compatibility, right? If we add this change into the language, we don't want to break existing code. And that sort of constrains us in what we can do. Yeah. So I think the last thing that I wanted to talk about is what Multicore OCaml brings for the Tezos ecosystem. Firstly, I want to say thank you to the Tezos Foundation for doing Multicore OCaml development work. Right, Multicore OCaml is a long-term project, right? And it's great to see Tezos investing in long-term projects that will eventually help Tezos. Concretely, Tezos is a heavy user of LWT, right? As the concurrency library. Today, we have a parallel version of LWT where we take LWT preemptive tasks and run it on a different domain. So if you are a current user and you have some tasks that you can parallelize, you can use this library to parallelize your tasks very cheaply without changing the entire. But where we are heading is this development of this direct style asynchronous IO library that I had linked before, right? And the hope is that we can bridge this gap between async and LWT that we have in the community today, right? If you pick async or LWT, you have to sort of go with one. And we are hoping that this direct style asynchronous IO library, thanks to effect handlers, which is sort of separates out the interpretation from the declaration, we can actually bridge the gap, and we can sort of come up with the good semantics that balances both. And we are also working with the Ermin team. Ermin is this library which is a storage layer of Tezos. We are working with them to parallelize Ermin, which will directly benefit Tezos ecosystem. And we are planning to build an end-to-end multi-core Tezos demonstrator sometime in the middle of 2021. Right, so I think initial work is apace, and we want to see how far we can push. Right, Tezos is an excellent demonstrator for us for pushing multi-core, and we hope to see that we can achieve something great with this demonstrator. That's all I had to say today, and thank you for listening. You can install Multicore OCaml with this very long command, but this sort of installs the Multicore OCaml compiler, brings in all of the packages that we have, and I have added some links underneath. And we have a paper which is published in ICFP 2020 that describes the parallelism bits. We also had an older paper that describes the effect handlers, all of which are linked below. Okay, so I will take questions from the audience. So the first question is, how do you check linear use of one-shot continuations? So linear use is checked dynamically. Today, if you resume the same continuation twice, you just get the continuation already taken exception, right? We don't have linear types yet. I'd love to have linear types, but that would be an entirely different language.
Thank you, Casey. We'll wait a little bit to see if there are some more questions. Don't hesitate to ask them in the stage chat. In the meantime, do you can you indicate sort of so these are the main places to read about the current work. I think there is also a thread on Discuss, like some regular updates on Discuss. And are there other places that we can sort of like reach out and ask questions and contribute to this effort?
Yeah, good point, Raphael. So we publish Multicore monthlies every month on discuss.ocaml.org, which sort of tracks the Multicore progress. I think the best place to reach out is the OCaml Multicore issue tracker, the GitHub repo. And we have a bunch of libraries under Multicore OCaml org. Do try it out. We made it easy to install it as an OPAM switch today. And we are already seeing a lot of bug reports from the community, and do keep it coming. Right? And the other thing that I would like to throw out is if you have a benchmark today, just a sequential benchmark, right? For OCaml, you should think about contributing to the Sandmark benchmark suite, which is also linked through the Multicore OCaml org. And what we're trying to build is a representative set of benchmarks that can sort of that will help us tune the Multicore OCaml implementation, right? If you want your programs to go fast on future OCaml, make sure you add a program, there. Otherwise, you might miss out. Okay, there are two questions there. The first question is, will there be some form of effect polymorphism in the type system? Yes, the plan is to have effect polymorphism. I am not the expert for answering questions on effect polymorphism, but yes, there is some form of effect polymorphism. I think what makes adding effect handlers in OCaml particularly difficult is abstraction, right? Many of the languages languages that propose effect handlers don't have a module system, right? Don't have signatures, so they don't have abstract types, and that makes it particularly difficult to marry effect system into OCaml. And I think we've made a significant amount of progress with that. So I think I'll take the next one. Are effect stacks dynamically extensible, or is it possible to get stack overflow if you don't allocate one large enough? Excellent question. So what I didn't mention is that our stacks are dynamically grown. So we start with a very small stack initially, and the stack is, if I remember correctly, 32 words in size, and we keep growing the stack, doubling the size whenever we hit the limit. we actually insert a Stack Overflow check in the OCaml functions. And the numbers that I showed you includes the Stack Overflow checks, right? And what we observe is that if you are clever about where we place the Stack Overflow checks, we do some optimization to eliminate many checks, we can actually make it work seamlessly. Yeah, really good question. So if I need a delimited continuation, should I use DLMCC or Multicore OCaml? You should use Multicore OCaml because I implemented it. But DLMCC is a good project. So we wrote a paper earlier called F directly in OCaml, which sort of implements the F language semantics in OCaml using delimited continuations. There we show the performance difference between DLMCC and Multicore OCaml continuations. You can have a look yourself, right? So Multicore OCaml delimited continuations are much faster. So I recommend using Multicore OCaml continuations, delimited continuations. So what are the most broken, most scary libraries that are out there that are not working with Multicore? Surprisingly few these days, I should say. So for a long time, we did not have system support. Systthreads are these way to create multiple kernel threads, all of which share a runtime lock around the OCaml runtime. So this caused enormous pain for us. We have Dune working, which uses systthreads in a non-trivial way. That's a large library. We have Corp working, I mean, that worked out of the box. I think increase there are fewer and fewer broken libraries, scary libraries, right, that don't work with Multicore OCaml. If there's one, we should know, right? And we have a branch called one thing that often breaks is the extension. Because we extend the Multicore OCaml syntax with syntax for effect handlers, PPX extensions don't work out of the box. PPX will complain that, oh, I see something which I shouldn't see. So for this reason, we have a branch in the Multicore OCaml repository, which I pointed to in the slide, called FX syntax. And all it does is it removes the FX syntax from Multicore OCaml, leaves all of the bits, rest of the bits in. So with that, we've been able to build a significant portion of the OPAM ecosystem with Multicore OCaml. So we are very happy that it's working out. So will it be possible to make parallel C externals aware of OCaml GC? For instance, OCaml values in C threads. Good question. So let me try to ask this. If you're, it should work out of the box. I think what you need to do, so we don't break the C API, right? That was one big thing that we described in the retrofitting parallelism to OCaml paper, the ICFP 2020 paper, where we had earlier that broke the C API, and we couldn't. You had to manually go and refactor your API. And the reason why we moved to the current scheme that I described today is specifically not to break C API, right? So if you have OCaml values in C threads, they should just work. If you have the same value across multiple C threads, you need synchronization. You can add synchronization either in C or OCaml, but the API just works out, right? This is it's a racy access, but it just works. Yeah, that's that question. That was the last one that I see on the chat. If you have more questions, I'm happy to answer.
Okay, we will one more question coming. And if you have some more, don't hesitate to type them in the chat. And once we are done with the queue, we'll just wrap it up. So the question is about concurrency-related bugs, and yeah.
Okay. So let me. So the question is. It's a wonderful question. I think I spent. As I mentioned, I mean, as Rafi mentioned, the bio I've been building multi-core languages for a while now, and I should have probably spent half of my professional life debugging bugs, right? And the question is, what sort of tools do you use to fix bugs, right? We've had several difficult GC bugs to debug. A wonderful tool called RR, right? I hope that none of my users need to use RR, because if you RR is a replay debugger built on top of GDB, right? It's excellent. It was originally from Mozilla. It's still being developed. So what RR lets you do is to run your program, record a trace, and then replay the program backwards, right? So you can go from a segmentation fault back to the source of the bug, and you can use all the GDB's features, hardware watch points, and so on. So RR has been excellent for debugging multi-core bugs. I think the question is about what techniques and methodologies do you learn? I learned a lot about how not to mess up the GC, right? So if you write down the GC invariants properly and then start working, I think it will save a lot of difficulties. But for the OCaml programmer, right? So the hope is that the abstractions that we provide, async, await, and parallel for, should make it easier to write parallel programs where you don't have to do this sort of debugging, the low-level debugging, right? And I really hope that's the case. We also have a library called reagents, which I haven't talked about here, which gives you transactions on top of Multicore OCaml. And these software transactional memory transactions are more efficient because they compile down to lock-free implementations. That is perhaps for another day. But using these high-level abstractions, I hope that none of my users ever have to sink down to the level of RR.
Okay. Thank you very much, KC. Looking forward to at some point using Multicore OCaml, hopefully very, very soon. Thank you, everyone, and have a nice evening.